All right, so today we're going to talk about how we might multiply two vectors together, which is much less obvious than how we add and subtract them. So, in fact, there are several ways we could define multiplication between vectors, and in fact, several ways that we will. Today we'll talk about one called the dot product or scalar product. And so the goal is to define a way of multiplying vectors together that gives us a scalar. And instead of just giving you the definition, like many books, let's spend, 5 minutes or so walking through sort of an outline that shows where the definition comes from. All right, so a key thing is that we want this new vector product, or this scalar product, to satisfy basic rules of arithmetic. Okay, so one example of this rule is the associative property, that if I have a scalar c times a vector a dotted with a vector b, that c should be able to come outside the product, all right? That it should be able to look like this. The c comes out and you have c times a dot b. And that's the same as a dot c times b, all right? All three of these quantities should be the same. We also wanted to satisfy the distributive property, that if I have a sum of two vectors, b dot plus c, that a dot b plus c should be a dot b plus a dot c. Ideally, we'd like this to satisfy the commutative property so that it doesn't matter what order I take the vectors in the multiplication. And finally, suppose we have two vectors and a vector, we multiply it by itself. We'd like somehow the result to be related to the square of something. Since it has to be a scalar, we can sort of choose that to be the square of the length of the vector. That's kind of a natural choice of how to set up the dot product. So these are very standard things, and if the dot product didn't satisfy these things, you would not be very happy about it, because this would really mess up everything we think we know about arithmetic. It turns out that these are enough to completely define the definition of the dot product. All right, so we start by drawing sort of a triangle here. We have a vector b and a vector c, and the sum of these two vectors equals a. Right, so a equals b dot c. We can move this b to the other side to get the expression a minus b equals c. And then you say, okay, suppose we dot both sides with c. And that's going to give us a magnitude of c squared over here. So we can take both sides and dot it with c. Now we have a minus b dot c is c dot c. But since this c right here equals a minus b, then this c can be replaced with a minus b as well. We're sort of just playing around a little bit here, but these are all completely valid operations. It might not be clear why we would want to do them, but it turns out that by doing this carefully selected set of operations, we're going to get something really neat up here. Because now we're going to use the distributive property on this thing right here. We're going to FOIL this out. A dot A minus A dot B minus B dot A plus B dot B. We're going to use the commutative property to say that this A dot B is the same as this B dot A, and that gives us this line right here. And now we're going to use the magnitude property. A dot A becomes magnitude A squared, B dot B magnitude B squared, and C dot C magnitude C squared, minus 2 A dot B left over here in the middle. So all of the dot products have gone away except this a dot b right here. Of course, a dot b is the thing we're trying to understand. And we have this relationship here between the dot product a dot b and the magnitudes of these vectors a, b, and c. It turns out that looks remarkably like the law of cosines, which is true for any triangle, and defines the length of one side equal to the sum of the squares of the other side minus 2 times the magnitude of those two sides times the cosine of the angle between them. So we got this result here from basic properties of arithmetic applied to our as yet undefined dot product. And we have this result here from geometry, the law of cosines. So it immediately follows that this gives us a definition of the dot product. That this thing here, the 2a dot b, is the same as this thing right here, 2ab cosine theta, and that gives us that a dot b must be magnitude a, magnitude b, cosine theta. whether you see it or not, this is a definition of the dot product. The definition of this scalar product of two vectors a and b is the product of the magnitudes times the cosine of the angle between them. And so if I have two vectors, we always choose the smaller angle between them to go right here in theta. All right, now this is what we call a geometric definition of the dot product, or I sometimes like to call it an intrinsic definition of the dot product. This does not depend on the coordinate system. We haven't said anything about a coordinate system yet. It gives us a physical meaning for what the dot product is. Now we'll proceed to what most books give you, which is a formula for computing the dot product, all right? Which is different than the geometrical meaning of the dot product. So we remember that any vectors, a and b, I've forgotten some of my vector signs here, can be broken down into a sum of basis vectors, a1i, a2j, a3k, and the same for b. So now let's apply our arithmetic properties to the dot product of these two things. A dot b is this long thing here, dotted with this long thing here. And then we want to make sure that the distributive property applies. So this is like a 3-term times 3 terms, which is sort of like FOIL, gives you 9 terms here. That's quite a bit. However, it turns out that a bunch of these terms vanish. All right, what did we just learn about the dot product? The dot product is magnitude A, magnitude B times the cosine of the angle between the vectors. I dot I, this term, these are both magnitude 1, and the angle between them is 0. Cosine of 0 is 1, and so you get 1 times 1 times 1. So this term survives. You get A1, B1. But what about this term right here, I dot J? I points in the x direction, and j points in the y direction, and the angle between them is 90 degrees, and the cosine of 90 is 0. So I dot j equals 0. This is a very important property of the dot product, that when you have perpendicular vectors, the dot product is 0. And so this term vanishes. Similarly, I dot k is 0 because the angle between them is 90. J and I are perpendicular, j and k are perpendicular, k and I, k and j, these all vanish, all 6 of these. I dot I is 1, j dot j is 1, and k dot k is 1. And so finally we get a formula for the dot product in Cartesian coordinates. A dot b is a1, b1, a2, b2, a3, b3. You just multiply term by term the components of the two vectors and then add them up at the end. This is where most books start. I want to say a little bit more before we do an example, which I briefly mentioned. Ideally, this could have gone earlier, but it's a very, very important property of the dot product. Probably the most well-known property of the dot product. That if two vectors, a and b, are perpendicular, then the angle between them is 90 degrees, and because the cosine of 90 degrees is 0, then this dot product always vanishes and you get 0. Okay, so this really common property, the dot product of two vectors is 0 if and only if the vectors are orthogonal. If you calculate the dot product and you get 0, then you know the vectors are orthogonal. Likewise, if you know they're orthogonal, you know their dot product is 0. All right, that's kind of a lot of talking, a lot of general stuff. This is a great time to sort of pause the video, go back over your notes, write some questions if you have any, but we'll go ahead and do a couple of examples. So here's two vectors, 3, 4, 6, negative 4, 3, negative 4. Compute the dot product. Very simple question. So all I do, 3 times negative 4 plus 4 times negative 3 plus 6 times 4. I add all that up. I get negative 12 plus 24, 0. What does that tell me? I just computed arithmetically the dot product. I got 0. That tells me that the vectors are orthogonal. So this is an example of using the dot product as a test for orthogonal vectors. Here's another pair of vectors, 3, 4, and 5, 6. If I've sketched them over here, they're kind of pointing in the same direction. I can compute their dot product. This is just in 2 dimensions now. 3 times 5 plus 4 times 6. That gives me 39. And just for being a little interesting, we can sort of play around with this a little bit more. We can say, well, we get 39. What's the magnitude of A? And we can plug that in and we can see that it's 5. What's the magnitude of B? We can plug in the magnitude formula and get this square root of 61. And so what does this tell us? We now have A dot B and A and B. We can use the formula, the geometric meaning of the dot product. Way up here, we can solve for cosine theta. Cosine theta is A dot B over magnitude A magnitude B. So another thing we can do with the dot product is determine the angle between two vectors. We plug that in, 39 over 5 times root 61. We do a little bit of arithmetic, or sort of approximating here, and we get this to be almost 1. 0 is an angle that gives a cosine of 1, and so that tells us these vectors are almost parallel. This wasn't an exact calculation. We could have plugged this into a calculator, used the inverse cosine button to tell us exactly what the angle was. Here we just showed that they're close to parallel, which you can kind of see just from drawing the picture. It's another great place. We're kind of moving on now to a new topic. It's a great place to pause the video, maybe look at a homework problem or two, and write any questions you have in your notes. Another very useful thing we can do with dot products turns out to be something called projection, projecting one vector onto another. So we start with a really simple example. We say, go back to last lecture where we're talking about breaking a vector into its components. So here's this shorthand bracket form, and that's equal to a1i plus a2j. If we imagine sort of shining a flashlight in this direction, then it would cast a shadow of this vector along the y-axis, and it would be equal to a2j. So second line here, a2j is what we call the projection of the vector A onto the y-axis. Whenever you see this word projection, you can think of shining a flashlight and looking at the shadow. Likewise, if we shine a flashlight down in this direction, it will cast the shadow here along the x-axis, which is a1i. That's called the projection of A onto the x-axis. Okay, that's an interesting definition. But now we're going to connect this to dot products. So if we remember these unit direction vectors, I is 1, 0, and j is 0, 1, we can see that a dot I is the vector a1, a2 dotted with 1, 0. That just picks off the value a1 here. And that's what a1 or a dot I is. Likewise, a dot j, because the j vector is 0, 1, that picks off the value a2 in the vector A. And so a dot j is a2. And these are precisely the lengths of these two shadows in the x direction and the y direction. All right, so that tells us something important, that the dot product with a unit vector gives us the size of the projection in that direction onto that unit vector. All right, our book calls this number, which is a scalar, these are scalar numbers, the length of these projections. It calls these scalars components. All right, so the component is the length of the projection. So that's fine, projecting onto the x-axis and the y-axis. That seems hopefully to make basic sense. But you can get a little more fancy. You can say, well, what if I want to take a vector b and I want to project it onto another vector a, which might not be a coordinate axis. So here's my vector b. I want to project it onto this vector a, and so what I'm really looking for is this vector here, which I've labeled x. What is the length of that vector, or what is the vector itself? The length of the shadow, or the vector describing the shadow. So this ends up happening quite frequently, and again, we can use dot products to do it. So as it says here in the notes, the length of this vector x is called the component of the vector b onto A, right? The length of the shadow on A. If you shine a flashlight down in this right angle direction that's perpendicular to A. Okay, so one way we can go about this is to think about it in terms of trigonometry. So what is the length of x? If we call this right here length b, then the length of x is just length b cosine theta. That's a basic trigonometric relationship. But cosine theta is a dot b over magnitude a magnitude b. We saw that higher up. And then this b cancels the 1 over b magnitude in the denominator, so we're left with a dot b over magnitude a. Or if you like, rearranging this a little bit, b dot a over its magnitude. But then what is this? This is just the unit vector version of a, which we've written a hat in the past. So this right here is a very nice generalization of what we wrote up above, that to get the length of the component of x, the projection of b onto a, we just dot b with the unit vector version of a. So make a the target of the shadow projection into a unit vector and dot it with b, and that's the length of the shadow. All right, now you might also ask yourself, that's a nice formula for the length of the shadow, but what if I want a vector description of the shadow or the projection? How could I get that vector? Well, we already have its length right here. This is its length. And to get a vector version of that, we just multiply it by a unit vector. Again, this right here, the unit vector version of a. So it'll be b dot a hat times a hat is the vector version of the projection. Okay, so this is called the component. This is called the projection. They both have the same length. One of them's a vector, one of them's a scalar. So, again, kind of a lot of talking. Let's do an example. Here's a pair of vectors. Find the component and the scalar and vector projections of b onto a for two sort of arbitrary vectors here. A is 1, 1, b is negative 1, 0. So here's a, and we want to project b onto a. That's going to be obtained by shining a flashlight in this direction. And here's a right angle. And this green arrow here is going to be the vector projection of b onto a. And the length of that green arrow is going to be what we call the component. So you often calculate these things together regardless of what the problem asks. You just go ahead and calculate both of them. What is the component? It's b dotted with the unit version of a. The unit version of a is 1, 1 over its length, which is 1, 1 over the square root of 2, dotted with b, which is minus 1, 0. And this is a simple b, and so it just picks off the first component of a, and so we get minus 1 over root 2. That's the length of that vector. Now how do we turn it into an actual vector? To get the actual green vector there, we just multiply that length times, again, the unit version of a over its magnitude. So we get minus 1 over root 2 times, again, 1, 1 over root 2. And that gives us negative a half, negative a half. The last part of this lesson is a simple application, a sample application of dot products, which is work. All right, a physics concept. You may have heard of this formula in different sorts of contexts, that work equals force times displacement. It's a measure of the energy expended to move something from one place to another. That may be something you remember, but really, as we saw before in the first lecture, both forces and displacements are vectors. Okay, so we need a scalar. The work is a scalar, and so it's a reasonable guess, and it's a correct guess, that work is actually a dot product of the force dotted with the displacement vectors. okay, which gives us magnitude f, magnitude d, times the cosine of the angle between them, which is a really important piece that is sometimes not mentioned in such detail depending on the level of your physics class. So for instance, let the blue arrow be the force field. Say this is gravity. Gravity is pushing down. All right? So if an object is displaced from a high position to a low position, it moves with the force field, and we say that the force field does work on the object, right? So positive amount of work. Work is positive because the angle between these two is 0, and so we have magnitude f, magnitude d, those are both positive, and cosine 0 is 1, and so the result is positive. On the other hand, if you displace something horizontally, technically, no work is done on the object because the angle between these two vectors is 90 degrees, which makes the cosine term 0. And so because these two vectors are perpendicular, the work is 0. Now you certainly may not feel like you're doing 0 work if you carry a heavy box horizontally across the room, but no energy has been expended between the initial and final position of the box. It has the same potential energy as long as you didn't lift it up or down. The energy you expended was simply your muscles contracting to struggle to keep this box at the same height as you moved it. But that is not the same as the work that is technically done on the object. Finally, if you, say, lift the object against the force field, you may be doing work, but technically, if this object moves against the force field, you say that the force field has done negative work. You are doing work against the force field, which technically means that negative work is done on the object. All right, so this final example, say a force of 100 newtons is exerted straight across horizontally to roll a boulder up a ramp with an 30-degree angle of inclination. How much work is performed on the boulder? We'll do this two ways. One, we'll just take the dot product. We can do this by getting a component version, a component form of this vector d. It says the problem is a 5-meter ramp, so this vector is 5 units long, and it has an angle of 30. And so if we use a little trigonometry, we can write that vector in the following form. 2.5 root 3, 2.5. The force field is straight to the right, 100 newtons, so 100 dot, comma 0. We dot them together, we get 250 root 3 joules. That's using the arithmetic definition of the dot product, and it required us to get the component form of the vector d. There's another way we could do this problem, though, which is to use the geometric definition of the dot product, which simply says the dot product is magnitude f, magnitude d cosine theta. Magnitude f is 100, magnitude d is 5, and then the cosine of 30 degrees is root 3 over 2. We do the same calculation, we get the same answer. So we've covered a lot of ground with this lecture. The first couple lectures will cover a lot of ground. The most important points of the lecture are the orthogonality property. The dot product of perpendicular vectors is always 0, and if vectors have a 0 dot product, they are orthogonal. Another really important part of this lecture is the geometric interpretation of the dot product, from which the orthogonality property follows. It gives you a way of calculating the dot product sometimes without using the component form. It also gives you a way to interpret the dot product. It also gives you a way to calculate the angle between two vectors, which is otherwise a pretty tricky proposition. And finally, the most commonly used, though least physically insightful, is the simple calculation formula for the dot product in Cartesian coordinates. So those are the main three things to get out of this lecture.